In abstract algebra, a valuation ring is an integral domain D such that for every element x of its field of fractions f, at least one of x or x minus 1 belongs to D. Given a field f, if D is a subring of f such that either x or x minus 1 belongs to D for every non-zero x in f, then D is said to be a valuation ring for the field f or a place of f. Since f in this case is indeed the field of fractions of D, a valuation ring for a field is a valuation ring. Another way to characterize the valuation rings of a field f is that valuation rings D of f have f as their field of fractions, and their ideals are totally ordered by inclusion, or equivalently their principal ideals are totally ordered by inclusion. In particular, every valuation ring is a local ring. The valuation rings of a field are the maximal elements of the set of the local subrings in the field partially ordered by dominance or refinement, where dominates if in every local ring in a field K is dominated by some valuation ring of K, an integral domain whose localization at any prime ideal as a valuation ring is called a proof domain. Examples: any field is a valuation ring. Z, the localization of the integers z at the prime ideal, consisting of ratios where the numerator is any integer and the denominator is not divisible by p. The field of fractions is the field of rational numbers Q. The ring of meromorphic functions on the entire complex plane which have a Maclaurin series is a valuation ring. The field of fractions are the functions meromorphic on the whole plane. If f does not have a Maclaurin series, then 1, f does. Any ring of p-adic integers zp for a given prime p is a local ring, with field of fractions the p-adic numbers qp. The integral closure zpcl of the p-adic integers is also a local ring, with field of fractions qpcl. Both zp and zpcl are valuation rings. Let K be an ordered field. An element of K is called finite if it lies between two integers n less than x less than m, otherwise it is called infinite. The set D of finite elements of K is a valuation ring. The set of elements x such that xd and x minus 1d is the set of infinitesimal elements, and an element x such that xd and x minus 1d is called infinite. The ring F of finite elements of a hyperreal field *R is a valuation ring of *R. F consists of all hyperreal numbers differing from a standard real by an infinitesimal amount, which is equivalent to saying a hyperreal number x such that minus n less than x less than n for some standard integer n. The residue field, finite hyperreal numbers modulo the ideal of infinitesimal hyperreal numbers, is isomorphic to the real numbers. Definitions. There are several equivalent definitions of valuation ring. For a subring D of its field of fractions K, the following are equivalent. For every non-zero x in K, either x in D or x minus 1 in D, the ideals of D are totally ordered by inclusion. The principal ideals of D are totally ordered by inclusion. There is a totally ordered abelian group gamma and a surjective group homomorphism nu K times gamma with D equals x in K times nu 0, 0. The equivalence of the first three definitions follows easily. A theorem of states that any ring satisfying the first three conditions satisfies the fourth. Take gamma to be the quotient K times D times of the unit group of K by the unit group of D, and take nu to be the natural projection. We can turn gamma into a totally ordered group by declaring the residue classes of elements of D as positive. Even further, given any totally ordered abelian group gamma, there is a valuation ring D with value group gamma. From the fact that the ideals of a valuation ring are totally ordered, one can conclude that a valuation ring is a local domain. and that every finitely generated ideal of a valuation ring is principal. In fact, it is a theorem of Krull that an integral domain is a valuation ring if and only if it is a local Bezout domain. It also follows from this that a valuation ring is Noetherian if and only if it is a principal ideal domain. In this case, it is either a field or it has exactly one non-zero maximal ideal. Such a valuation ring is called a discrete valuation ring. A value group is called discrete if it is isomorphic to the additive group of the integers. And a valuation ring has a discrete valuation group if and only if it is a discrete valuation ring. Very rarely, valuation ring may refer to a ring that satisfies the second or third condition but is not necessarily a domain. A more common term for this type of ring is uniserial ring. Construction. For a given totally ordered abelian group gamma and a residue field K, define K equals K to be the ring of formal power series whose powers come from gamma. That is, the elements of K are functions from gamma to K such that the support of each function is a well-ordered subset of G. Addition is pointwise, and multiplication is the Cauchy product or convolution. That is the natural operation when viewing the functions as power series. With the valuation nu for f and k is defined to be the least element of the support of f, that is the least element g of gamma such that f is non-zero. The f with nu 0 form a subring D of k that is a valuation ring with value group gamma, valuation nu, and residue field k. This construction is detailed in, and follows a construction of which uses quotients of polynomials instead of power series. Dominance and integral closure. The units, or invertible elements, of a valuation ring are the elements x such that x minus 1 is also a member of D. The other elements of D, called non-units, do not have an inverse, and they form an ideal M. The ideal is maximal among the ideals of D. Since M is a maximal ideal, the quotient ring D, M is a field, called the residue field of D. In general, we say a local ring dominates a local ring if and, in other words, the inclusion is a local ring homomorphism. Every local ring in a field K is dominated by some valuation ring of K. Indeed, the set consisting of all subrings R of K containing A and is non-empty and is inductive, thus, has a maximal element by Zorn's lemma. We claim R as a valuation ring. R is a local ring with maximal ideal containing bimaximality. Again bimaximality, it is also integrally closed. Now, if, then, bimaximality, and thus we can write, since is a unit element, this implies that is integral over R, thus is in R. This proves R is a valuation ring. A local ring R in a field K is a valuation ring if and only if it is a maximal element of the set of all local rings contained in K partially ordered by dominance. This easily follows from the above. Let A be a subring of a field K in a ring homomorphism into an algebraically closed field K. Then F extends to a ring homomorphism, D some valuation ring of K containing A. If a subring R of a field K contains a valuation ring D of K, then, by checking definition 1, R is also a valuation ring of K. In particular, R is local and its maximal ideal contracts to some prime ideal of D, say. Then since dominates, which is a valuation ring since the ideals are totally ordered. This observation is subsumed to the following. There is a bijective correspondence the set of all subrings of K containing D. In particular, D is integrally closed, and the Krull dimension of D is the cardinality of proper subrings of K containing D. In fact, the integral closure of an integral domain A in the field of fractions K of A is the intersection of all valuation rings of K containing A. Indeed, the integral closure is contained in the intersection, since the valuation rings are integrally closed. Conversely, let X be in K but not integral over A. Since the ideal is not, it is contained in a maximal ideal. Then there is a valuation ring R that dominates the localization of it. Since the dominance is used in algebraic geometry, Let X be an algebraic variety over a field K. Then we say a valuation ring R and has center X on X if dominates the local ring of the structure or sheaf at X. Ideals in valuation rings. We may describe the ideals in the valuation ring by means of its value group. Let gamma be a totally ordered abelian group. A subset delta of gamma is called a segment if it is non-empty, and for any alpha in delta, any element between alpha and alpha is also in delta. A subgroup of gamma is called an isolated subgroup if it is a segment and is a proper subgroup. Let D be a valuation ring with valuation V and value group gamma. For any subset A of D, we let B the complement of the union of an in. If I is a proper ideal, then is a segment if. In fact, the mapping defines an inclusion reversing bijection between the set of proper ideals of D and the set of segments if. Under this correspondence, the non-zero prime ideals of D correspond bijectively to the isolated subgroups of gamma. Example: the ring of p-adic integers is a valuation ring with value group. The zero subgroup of corresponds to the unique maximal ideal and the whole group to the zero ideal. The maximal ideal is the only isolated subgroup of. The set of isolated subgroups is totally ordered by inclusion. The height or rank R of gamma is defined to be the cardinality of the set of isolated subgroups of gamma. Since the non-zero prime ideals are totally ordered and they correspond to isolated subgroups of gamma, the height of gamma is equal to the Krull dimension of the valuation ring D associated with gamma. The most important special case is height 1, which is equivalent to gamma being a subgroup of the real numbers under addition. A valuation ring with a valuation of height 1 has a corresponding absolute value defining an ultrametric place. A special case of this are the discrete valuation rings mentioned earlier. The rational rank RR is defined as the rank of the value group as an abelian group. Places. The reference to this section is Zariski-Samuel. A place of a field K is a ring homomorphism P from a valuation ring D of K to some field such that, for any, the image of a place is a field called the residue field of P. For example, the canonical map is a place. Example: let A be a Dedekind domain and a prime ideal. Then the canonical map is a place. We say a place P specializes to a place P, denoted by if the valuation ring of P contains the valuation ring of P. In algebraic geometry, we say a prime ideal specializes to if the two notions coincide. If and only if a prime ideal corresponding to P specializes to a prime ideal corresponding to P in some valuation ring, it can be shown. If, then for some place Q of the residue field of P. If D is a valuation ring of P, then its Krull dimension is the cardinality of the specializations other than P to P. Thus, for any place P with valuation ring D of a field K over a field K, we have, if P is a place and A is a subring of the valuation ring of P, then is called the center of P in A.